So we're going to look at a little video on complex numbers. And complex numbers are going to be one of the fields that we are going to be using in this class. And complex numbers, as you go on in mathematics, will become more and more prevalent. Now, with complex numbers, we have two things that we should know. One is that the operations we use, the addition and multiplication operators, work in a very similar way and are based upon the multiplication and addition operators from the real numbers. The second thing that we should note is this term I. Complex numbers are built on this term I, which is the square root of -1. So if we look at all of our numbers and we square them, our negatives become positives and our positives remain positive. But if we wanted some number that when squared goes to our negative real numbers, in order to get that number, we have to introduce this term I. And then I, when we square it, will give us -1. And that's the motivation for complex numbers. That's where they come from. Now, we need to note that I is not a real number. It plays a very important role within mathematics. And when we say it's not a real number, it doesn't lie on the real plane. It's a number, it's something we can work with, but it's not real. Okay? Now, complex numbers are of the following form. Z equals A plus BI. Here, A, which is an element of the real numbers, is the real part of the complex number, or RE of Z. And B, which is also a real number, is the imaginary part of Z, or IM of Z. So these values A and B, they're both real numbers. But when we combine them in this way, we get a complex number. Now, when looking at complex numbers, it's often helpful to have a visualization to help us understand. And what we have is this here is this is 1i, this is 2i, then we have -1i and -2i. So what we have is if I have, let's say, 1 plus 2i, that's 1 along the real axis and 2 along the imaginary axis. And if we think of our vectors, the vector 1, 2, it'd be the exact same. Our resulting vector is this piece here. That's our resulting vector. And that vector is 1 plus 2i. Now, as we have mentioned, complex numbers form a field. But with what operations? What are the operations we use? And the operations that we use are the standard addition and multiplication operators. So addition, if we look at Z1 plus Z2, this is going to give us A plus BI plus C plus DI. Now, our standard addition operators are associative and commutative. So because of this, we get A plus BI plus C plus DI, which equals A plus C plus BI plus DI, which is equal to A plus C plus B plus DI, which itself here is a complex number. We can see that this is a real number. Our A plus C is a real number, and B plus D is a real number. So we get a complex number when we add the two numbers. Okay, so we're closed under addition. It is an important property about our field. If we recall, if we look at our field, we have two numbers. When we combine them, we get another element from our field. So we are closed under addition. And if we look at multiplication, Z1 times Z2, this is equal to A plus BI times C plus DI, which we are going to expand in the typical way to give us AC plus ADI plus BIC plus BIDI, which is equal to AC plus CDI plus BCI plus D or BDI squared. And this I squared is going to become -1. So we get AC minus BD plus CD plus BC times I. And once again, we get a complex number. So we're closed under multiplication. And this is how we could multiply them. We could figure out what the A and the B terms is, and we can memorize this formula, but that's not the idea. The idea behind this is we've shown that it's closed under addition and closed under multiplication, meaning two complex numbers. When you add them, you get a complex number, or when you multiply them, you get a complex number. The other idea is the way in which we add them is the way in which we are used to adding numbers. And the way in which we multiply is similar to what we're used to. And you can think of it as expanding the roots of a polynomial. But now that we have the addition and the multiplication, we want to show that it's a field. So what I'd highly encourage you to do is go through the axioms of what it means to be a complex number and prove to yourself that it satisfies the properties.